to run for at least a couple hundred years. Okay, this is a video, but it's fine. Yeah, all is just a drop. Okay, I won't be showing it to you. And now, after we looked upon the effect of the time scale of the experiment on the glass transition, let's look upon a definition. How do we define, let's say, the glass transition in terms of free volume? Okay, and free volume in general is the volume within a polymer sample that is not occupied by polymer molecules. Okay, so it is associated with the end of the polymer chain, because obviously at the end of the polymer chain we will have more free volume. You can see here that there is more free volume here than there is, I don't know, here or here. Okay, so the free volume is associated with the end of the chain of a polymer. Okay, the end of macromolecular chains. Okay, so when we use this graph here to observe the cooling process from the liquid state, let's say, to the glassy state, so we have V0, which is the volume occupied by molecules. So this is standard, and of course at the glass transition we have a characteristic change of slope over here, and the shaded area has to do with the free volume. Okay, so when we lower the temperature, the free volume is reduced because the molecules stop moving. You realize that when we reduce the thermal energy, there is a reduction in the movement of the chain. And until we have a reduction of the movement of the chain, free volume remains high. And then once the chains get frozen, then the free volume remains constant, and that is this region. Okay, so here we have constant free volume, and above the glass transition temperature we have an increase of the free volume because the chains are actually moving, and because they're moving we have more statistical opportunities in order to observe higher free volume. Okay, and one of the most widely used methods to determine the glass transition is to observe the free volume as a function of the temperature of the experiment. So that is how fast do we cool, and how slow do we cool our polymer. And by fast, generally we mean rates in the order of 20 plus Celsius per minute, and slow we can say I don't know, 5 Celsius degrees per minute and lower. Okay, let me. And at 20 Celsius degrees per minute, we see that we have higher Tg. The reason for that is because the liquid has no time to relax. Okay, so if we cool it very fast, the polymer does not have enough time to equilibrate, to stabilize. Okay, and because it doesn't have enough time to stabilize, it displays a higher Tg. But because when we cool it slowly, that is I don't know, less than 5 Celsius degrees per minute. In this case, the liquid can relax or equilibrate, and by equilibrating, it takes up the properties of the next temperature. And obviously, the slower we measure the glass transition, the more accurate values of glass transition that we get. Okay, but it is very important to remember that the cooling or heating rate certainly affects significantly the glass transition temperature. And that is why we call a glass transition temperature a pseudo second order transition. And we will see that now. Yep, that is what we said. So if we go to the dynamics of glass transition, essentially there have been attempts to analyze the glass transition from a thermodynamic viewpoint, okay? And let's start with the simplest case where we have a first order transition where the free energy, the Gibbs free energy at transition is continuous, okay? But the derivative of the Gibbs free energy as a function of temperature at constant pressure, that is this ratio here, this derivative here, and this derivative here are discontinuous. Don't worry about these graphs. I won't about these formulas. I won't be asking you to remember any of these. So I just want you to remember that melting is a first order transition, while glass transition is a second order transition, and actually not a real second order transition, but a pseudo second order. Or pseudo means fake, okay? Not real. So in the case of melting, essentially, the first partial derivatives of the Gibbs free energy with respect to the relevant state variables, the state variables are volume, pressure, and temperature. These are the state variables. These provide discontinuities in the volume, the enthalpy, and the entropy. Okay, I don't want you to remember any of these formulas. Okay, don't worry about the formulas. In the case of, as I said, in the case of a second order transition, there is a discontinuity in the second partial derivatives. Okay, so here we have a second partial derivative. You can see. And but there is a continuity of both the free energy and the first pulsar derivatives. Okay, so there are no discontinuities in the volume, the enthalpy, or the entropy. That is what happens. That is what happens for a first order transition. But in this case, there are discontinuities in thermal expansion coefficient, compressibility, and heat capacity. Okay? So if we look upon these graphs that we saw earlier, this is the volume versus temperature for the melting point and the glass transition. Here we said the melting point is a first order transition. All I want you to remember from the thermodynamics of glass transition is what we will discuss in this slide, okay? Forget about the formulas in the previous slide. So the melting point, we said, it has to do with the crystalline region, okay? Here you can see that we have a step change. What does this mean? It means that a lot of heat is added to our polymer, to our material, without a temperature increase, okay? Of heat or of volume or of entropy, okay? And you realize, because above the melting, if we evaluate it, let's say, in terms of the entropy, above the melting point, we have the chains that are moving completely freely, okay? And what does the entropy show us? The entropy shows us how random is the movement of these chains, okay? How random the chains are moving. So above the liquid state, then we have a significant increase of the entropy at the melting point. And that is why we have this step change here. And that is why we have the melting point as a first order transition, okay? On the other hand, we said already that the glass transition is a pseudo second order transition. Of course, we said that it has to do with the amorphous region. And as you can observe, we don't have any jumps, okay? We don't have any discontinuities in this graph. Okay? The reason why we call glass transition a pseudo second order transition is because it depends on the heating rate, okay? We said already that depending on the heating rate, we can get different values of a glass transition. And it's actually a matter of of debate if we heat it at very, very low heating rates, how much is the minimum glass transition that we can achieve. But anyway, so pseudo has to do with the fact because it depends on the cooling rate. Okay. So let's go and look upon some a bit more interesting things. What are the factors that affect the glass transition temperature? Okay. What are the factors that we can take advantage of and we can tune the glass transition temperature? Or essentially, what are the structural characteristics of a polymer that can be utilized in order to understand the glass transition temperature? And that have to do with the chain length, the chemical structure, the side groups, the cross-linking, the molecular weight, and the plasticizer. So as you can realize, there are quite a few individual types of factors that can affect the glass transition temperature. So let's see them one by one. The chain length. The chain length, we already talked about the free volume, and the more free volume that we have, the lower temperature we observe for the glass transition, because if there is more free volume, there won't be needed so much thermal energy in order to induce this conformation, okay? If there is low amount of free volume, if the chains are generally packed in there, then we need more thermal energy in order to make them move more easy, because there is no enough space for the chains to move, okay? Because the free volume is associated with small chains, so small chains provide more free volume to the polymer. In this case, for short chains, we have lower TGs, but for long chains, we have higher TGs, okay? So TG for short chains is lower than TG for long chains. And it has to do with the chain ends. Short chains provide more chain ends, more free volume, lower glass transition temperature, okay? Of course, what is very, very important is the chain flexibility, okay? If there is high flexibility of the chain, that leads to lower TG, okay? So for higher flexibility, we have lower glass transition temperatures. However, as you know, there are groups that provide stiffening to the chains because of their strong bonds, and because of that, we have higher activation energy. What is higher activation energy? We need higher thermal energy to induce conformational changes. For the low materials, for the soft materials, we have activation energy that is lower. Well, if we have stiffening groups, we have higher energy and higher TGs, okay? And some of the characteristic stiffening groups is, of course, a carbon ring, a phenyl ring, which you know that it is like that, okay? Wait, no, let me put it like that. Okay, so we have alternating double carbon bonds between in a phenyl ring, and because of that, it needs a lot of energy to break these double carbon bonds down. Okay, the same applies for carbonyl groups or amide groups, which are much stiffer, much more stronger, let's say, in terms of the bond energies compared to normal carbon-carbon or carbon-hydrogen bonds, which are we have low breaking energies. Okay, these materials, sulfone or carbonyl bonds or amide bonds or phenyl bonds, have much higher activation energies. So if these materials are present in a macromolecular chain, that leads to an increase of the glass transition temperature. And can you please text me and let me know which are the in terms of sequence, which are the highest, from highest to lower glass transition temperature for this material? From higher to lower, okay? Based on what we just said, if the chain is flexible, then we have lower TG because the chain is already flexible, it can move already relatively well. We provide a bit of energy and then the chain starts moving, okay? Polymer group, very well. Let me check the materials. Yes, obviously, we have the TG of the PI polyimide being higher than the TG of polycarbonate, being higher than the TG of PET, and then we have the lowest TG of PE. But also PE, as you realize, there are quite different types of polyethylene. So different derivatives of polyethylene give it a glass transition that can range from, from minus 120 up to minus 30 Celsius degrees. So the TG in this case, minus 120 Celsius degrees. The TG of polycarbonate is relatively high, and you can see that we have carbonyl groups, we have phenyl rings or benzene rings over there. We have also some flexible, of course. These provide flexibility actually. So these generally reduce the TG. So yeah, this one has 150 Celsius degrees. The PI, the polyimide, as we said, is one of the most difficult polymers to fabricate, to process, because of you can see that the bonds are very difficult to fabricate, all of them. You have three phenyl rings in the main chain, you have carbon-oxygen bonds, you have nitrogen bonds. So the TG can be higher than 400 Celsius degrees. And that is why we use it for aerospace applications. It is extremely expensive as well. And not extremely, it is expensive as well, of course, compared to several other polymers. And finally, the PET has a glass transition of around 70 Celsius degrees, okay? You can see that it obviously has higher glass transition than the PE, much higher, of course, because you can see that there are carbon-oxygen bonds, there is a phenyl group over there, and so on. The reason why polyethylene has around 80 degrees difference between the glass transition of polycarbonate is because, firstly, it has much longer chain. Secondly, it has only one phenyl ring, and also it doesn't have any other double bonds over there, so it's much easier to break down the bonds, okay? Now, there are some kind of side groups, like this group, adamantine, which is a very large group, because essentially a big group like that just acts like a hook that catches on nearby molecules, okay? It's like you have a boat, and this acts like an anchor, okay? You have a boat like that, you have the anchor. So if this is very heavy, then it's more difficult for the boat to move. And the same applies for the polymer, okay? You need more energy. So you need more energy for the engine here, or you need more thermal energy in the case of polymer, in order to soften your material, okay? And of course, it has to do with the very high mass of this side group, because it makes the main polymer chain to move much slower. Okay, so for a normal polyether ketone peak, which has a high TG, 120 Celsius degrees, if you attach chemically this adamantine group to the peak, you can increase the glass transition for more than 100 Celsius degrees, okay? So you can realize how big the difference is just by adding a large group like this one. But of course, we have groups that don't behave the same with these very large groups, and the simple, or like adamantine, okay? And the simplest case of a side group can be methyl groups, let's say. So if we have a methyl group and we add more methyl groups, so we elongate our material, essentially, we elongate the chains. You can see this is longer, shorter, shorter, and shorter, okay? So if we have very long side groups like that, on top, on the bottom of the main macromolecular chain, what that does is essentially prevents the macromolecular chains from packing closely to each other. So instead of being packed like this, the chains are packed like this because you have the side groups here. And because you have these flexible side groups, these essentially reduce the glass transition temperature because they add more free volume to the polymer. Okay, so long flexible side groups lower the TG. They limit how closely the polymer chains can pack together, and generally more room between polymer chains. We said more free volume, lower TG. Okay. So if we look for the characteristic example of polymethyl methacrylate or PMMA, which is kind of a thermoplastic, you can see that the normal structure of polymethyl methacrylate has a glass transition of 100 to 120. By adding just one methyl group to PMMA, it makes this polyethyl methacrylate, of course, and polyethyl methacrylate has a glass transition of 65 Celsius degrees, which is 40 to 50 to 60 degrees difference compared to the previous material. Just adding one more methyl group, it reduces by 30 degrees, 35, and then just adding one more, again, we can reach a glass transition of 20. So just by adding, which is the simplest process in terms of chemical functionalization and polymerization, the addition of methyl groups, just by adding methyl groups onto a side chain of the polymer, we induce more free volume, and essentially we lead to the fabrication of a polymer that can have a glass transition in the order of 100 degrees lower compared to the primary polymer. Okay. So again, similar to previously, can you please text me what is the sequence of glass transitions for these materials? Polyethylene, polypropylene, and polystyrene is the most. That's a good point. If there is possible for alongside groups to form entanglements, yes, they generally can, but entanglements do not face significant problem. For the glass transition, we want the chains to start moving, okay, in order to soften. The entanglements, as we said, remain through the glass transition. So even if they form entanglements, it doesn't really affect significantly the glass transition. What it affects, though, is how long, in this modulus versus temperature graph, is how long this plateau here will be. The glass transition will remain unaffected, but if we have more entanglements, this plateau can be lower, or if we have lower amount of entanglements, this plateau can be shorter, okay? So that is increasing amount of entanglements. But generally, what I want you to remember is that when we have long side groups, that adds to more free volume, and more free volume leads to a lower TG. So a couple of answers: polystyrene higher than polypropylene than polyethylene. Of course, very easy and very straightforward. Okay, and for these three, I'd like you to remember. I'd like you to remember these values because these are. I'm pretty sure you come across these materials at least once in your day, okay? So just remember this. Polyethylene has minus 120, we said. Polypropylene can have around minus 15 Celsius degrees, but there are polypropylenes that have from minus, I don't know, 15 to minus 5, sorry. And polystyrene, you can see how much difference a very large side group makes, okay, because you can see that the main chain remains the same, okay? Just one small flexible group here, one small side group here makes the chain increase the glass transition, but one large group, it makes the glass transition in the order of 100 Celsius degree. And that is why we use polystyrene generally as a thermal insulator. Okay, it shows low thermal conductivity. Okay, let me check your answers. Yep, okay. Now, next, cross-linking. Actually, let's take a break now. Before I start with cross-linking, I'd like to point this out a bit more clearly. So let's take a break now, 10 minutes, and we continue in 10 minutes with a couple more factors affecting the glass transition temperature. So let's get started. Second part of today's course. And we have been looking upon the factors that affect the glass transition temperature. And one of the factors that affects significantly the glass transition temperature is cross-linking, okay? We use cross-linking in order to improve the properties of materials such as elastomers or epoxies, okay? That is rubbers or thermosets, okay? We have two different types of cross-linking. We have chemical or physical cross-linking. And chemical cross-linking can be a formation of covalent bonds or ionic bonds. And by physical cross-linking, we use a secondary polymer in order to induce a hard and soft phase. And usually it's used in thermoplastic elastomers. Let's see. So cross-linking in generally reduces chain mobility. So from a soft material, once we cross-link it, it becomes stiffer, okay? It becomes harder. So it generally affects the viscosity of the polymers. So by cross-linking, we create a three-dimensional network. Essentially, we have creation of 3D network of chains. And with the increasing of the amount of cross-linking, we have increase of the glass transition temperature, okay? So you can see three different types of situations between bonds between chains. So when we have linear chains, we have secondary bonds such as van der Waals bonds between the chains. So these are generally easy to break, and because of that, any low amounts of thermal energy can induce a transformation and passing through the glass transition temperature transformation of the conformations between the chains. For branched materials, we said that we can have a bit of different types of branches. We can either have very long branches, which generally reduce the amount of reduce the glass transition temperature, but also we can have branches or side groups such as the case of adamantine or some other cases where we attach long bulky side groups, and in this case we increase the glass transition temperature. And finally, with the cross-linked chains, we have a creation of 3D network of chains. We have creation of bonds. That is either physical or chemical bonds, which are more hard to break, and that leads to an increase of the glass transition temperature. Okay, so as we said, cross-linking essentially affects significantly the glass transition temperature of elastomers or materials in general, let's say, but elastomers or epoxies, and with increasing network density or increasing cross-linking. X-linking is a cross-linking, okay? With increasing degree of cross-linking, we have an increase of the glass transition temperature, okay? Now, there is an empirical equation that's provided by Florian Fox, two very significant scientists in polymer physics. And based on this equation, the glass transition of a temperature is affected by the molecular weight, but up to a molecular weight of 20,000, okay? So up to, let's say, 20,000, where is it? Around here. or a bit lower. Like here. So up to this point, there is a linear increase or kind of a parabolic increase of the glass transition temperature. But after that, it saturates, okay? It stabilizes. Saturation. Stabilization. Okay? So the Fleury-Fox equation is not very important. It is highly empirical, and it has to do with two parameters. That is the Tg infinity, which is the maximum glass transition temperature that can be achieved at theoretically infinite molecular weight. And K is another empirical parameter. So it's not a very serious equation. It's a very empirical equation, and you won't be needing to use it. If you need to use it, you should be provided with Tg infinity and this K parameter, and then it makes absolutely no point in using it. But indeed, the situation can be true for different types of polymers, such as polystyrene, up to a molecular weight of 20,000 grams per mole. That is grams per mole, okay? Up to 20,000 grams per mole. You can see we have a almost linear increase, and after that, we have the formation of this plateau here, where the glass transition essentially saturates, stabilizes. This is for polystyrene. Obviously, the molecular weight affects significantly all the properties of a polymer, and the glass transition temperature couldn't remain unaffected from the effect of the molecular weight. So essentially, what happens when we have a high molecular weight? When we have high molecular weight, we have either very long chains or a very large number of chains, or a very viscous material, because the weight of the chains are very long, okay? We said we have three different types of molecular weights: number average, weight average, and Z average, okay? And they depend on the number of chains, the weight of the chains, and the length of the chain. Anyway, the high molecular weight generally leads to a decrease of VF. What is VF? The free volume. And when we have a low amount of free volume, what does this mean? The chains do not have enough room in order to take new conformations. And because they don't have enough room to take more conformations, the Tg increases. Okay, so a high molecular weight generally leads to an increase of the glass transition temperature. Okay. Now, plasticizers. Plasticizers are very, very important substances in different types of polymer applications. Okay, and they're generally used because sometimes polymers have glass transitions that are higher than the ones that we like. Okay, and we want to just reduce the glass transition in order to make the polymer different, behave differently at certain temperatures. Okay, in order to manipulate the glass transition temperature, we use something. We use a chemical substance that is called a plasticizer. Okay, a plasticizer is a small molecule. Okay, remember that these small molecules or display low molecular weight, essentially. These are small molecules that get between the polymer chains and make them space from each other, okay? So you have the polymer chains that they are like that, and you use plasticizer here, you use another plasticizer here, and you open up the distance between the polymer chains, okay? By opening this distance between the polymer chains, what happens? We increase the free volume. And now we go all the way back to our discussion with the free volume. When we have a lot of free volume, the chains can slide past each other more easily. And when they slide past each other more easily, they can move around at lower temperatures than they would do without the plasticizer, okay? So by adding a plasticizer, the glass transition of a temperature is lower, makes a polymer more flexible, more pliable, and it's easier to work with, okay? What the plasticizer do is essentially lower weaken the intermolecular forces, okay? Establish polar attraction and reduce the cohesive forces, okay? They weaken the intermolecular forces. So all these forces here, these secondary forces, they cannot take place because we add more distance between the chains. So because they weaken the intermolecular forces, they decrease the glass transition temperature. Plasticizers often are added to semicrystalline polymers to lower the glass transition below room temperature. Okay, so in this case, the amorphous phase of the polymer will be rubbery at normal temperature, reducing the brittleness of the materials. Okay, generally, plasticizers have been used extensively in the automotive industry. And in the case they were used extensively, a number of plasticizers has been used extensively, but over the last few years, people have realized that some types of plasticizers are toxic and can cause health problems such as polychlorinated biphenyls. These were the most common plasticizers in the 80s and 90s, and then people discovered that these are toxic, okay, and they stopped using them. So yeah, plasticizers, the amount of plasticizer that we use, as you can see from this graph, and the amount of plasticizer we use is able to regulate the glass transition temperature, okay? So if we want to, let's say, for, what is this polymer? Has a glass transition temperature 160. Not sure. Maybe it's polycarbonate. What did we say earlier? What is the glass transition of? Yes, polycarbonate. So it's most probably a polycarbonate. I'm not taking a vow, but anyway. If this is a polycarbonate, we introduce different types of plasticizer and different contents, okay? And by adding plasticizer at different contents, you can see that we can tune the properties of the glass transition of our material. So if we add ethylene carbonate at 10 weight%, we lower the glass transition by 40 Celsius degrees, okay? If we want to lower it even further, we add 20% of ethylene carbonate. If we want to lower it just little, we add 2% and we lower it, I don't know, 15, 17 degrees. So the amount of plasticizer we add leads to different spacings between the molecules, and different spaces between the molecules lead to different glass transition temperatures. And polyvinyl chloride is a characteristic example, which normally has the modulus of PVC is around 1 to even 3 gigapascals sometimes, okay? But with the addition of a plasticizer molecules, this adds flexibility and essentially makes the material very soft, in the order of megapascals. And that is why PVC has been used in different type of very soft materials, such as, I don't know, these ducks that I use for when I'm bathing my daughter, or these cases for pens, or these very ugly coats or whatever. Of course, plasticizers do not only give us good properties, okay? So essentially, what happens with the plasticizer, they allow the polymer chains to slide past each other because they create space, okay? Create free volume between chains. However, I need to point out that even though the flexibility and the toughness of our materials increases with the amount of plasticizer, okay, because the flexibility for a thermoplastic, let's say, it looks like that, okay. So if we have a material that can elongate, the toughness is given by this region here. And if we don't have a plasticizer, maybe this material can break like that, can break here, okay? So we make the material elongate more, okay? However, by introducing the plasticizer, what we end up also getting is that we lower the melting point and we also lower the tensile strength. You can see that the tensile strength here is lower where in the case of plasticizer, okay? Here we have plastics. So again, with the introduction of a plasticizer, we increase the flexibility, we increase the elongation of our material, and by increasing the flexibility, we increase the toughness of our material. However, with increasing amount of plasticizer, we decrease the melting point and the tensile strength as well. Yep, that's what we said. So to sum up, for the factors that affect the TG, the chain flexibility, that is the intramolecular interactions, affect significantly the glass transition. Also, intermolecular interaction, chain distance, plasticizers, and so on. The chain length up to 20,000 grams per mole. And obviously, the time scale of our experiment affects the glass transition temperature. Now, let's look upon situations when we have polymers that are a combination of either two monomers or two polymers, okay? And when we have a combination, when we mix two polymers, we create a blend, okay? The blend can be miscible, so these polymers are compatible, so we can blend them easily, and there is no problem. The new material shows properties between the two of the original material. So if we blend polystyrene and polypropylene oxide, here we have a miscible blend, okay? And for the case of a miscible blend, we have compatible polymers, a molecular blend emerges, and in this case, we have a real mixture. The blend acts as a new material with only one single glass transition temperature. So this is the glass transition temperature. And of course, as you realize, the value of the glass transition temperature depends on how much of the two materials we will introduce. If we use, let's say, most of the polystyrene, then the glass transition will move this direction, okay? If we use, let's say, I don't know, 90% of PPO and 10% of polystyrene, then the glass transition will move towards this direction, okay? So, miscible blend, 1 TG. Okay, and in order to have a theoretical, let's say, a theoretical equation that can provide us with the value of the glass transition temperature for blends or for miscible or immiscible blends. No, sorry, for miscible blends, only for miscible. We have this Flory-Fox equation. And what does it tell us? It tells us that the inverse of the glass transition temperature of the blend, that is for the blend, okay, is given by the ratio of the weight of the one polymer over the glass transition of the one polymer plus the weight of the second polymer over the glass transition of the second polymer. Okay, it is a very simple equation, very straightforward. But as you can see in this graph here, these values, the black or red values that I messed up with, these are experimental values of the glass transition for the PMMA isotactic, syndiotactic polymethyl methacrylate blends. And you can see that with the increasing syndiotactic polymethyl methacrylate, we increase the glass transition temperature. And the linear fitting of these values here is based on the Fox equation. It can give us very good agreement with experimental values. Okay, you can see that the line falls absolutely on the experimental values, which says that generally the agreement of the Fox equation is very good, and it is very commonly applied to determine the glass transition in miscible polymer blends, and also as we will see in a bit, in random copolymers, because random copolymers also show 1 Tg. Okay. However, there is the situation where we don't have miscible blends. Okay, there is immiscible blend. So in this case, we have dispersion, or the blend acts as a kind of composite. Okay. So you can see that there are two phases in the blended polymer. Okay, there is the phase from the alpha polymer and the phase of the beta polymer. Okay, so when we have an immiscible blends, so in this case we have two glass transitions in the blended material. So we will have the glass transition of alpha and the glass transition of beta. Okay, so in this case, the highlighted curve of the blend essentially displays two glass transitions, the one glass transition of the one phase and the other glass transition of the second phase. Okay, so I want you to remember that immiscible blend two glass transitions. And obviously, again, what is the modulus here? That is determined by composition. That's specified as the modulus. Okay, the Plato modulus. Now, of course, besides blends, which is a very basic situation where essentially we melt two polymers and we combine them. Okay, we mix them. It's like making I don't know, something like cooking. What we can do in order to fabricate materials where we have a precise arrangement of monomers in the combination of the two materials is the fabrication of copolymers, okay, or copolymerization, where by copolymerization we combine two monomers in order to create the new materials. So for the case of, let's say, example SBr, that is styrene butadiene rubber. Styrene. We have a combination of butadiene monomer and styrene monomer. Okay, butadiene has a glass transition of -95 because it's elastomeric, and styrene has a glass transition of 90. Okay, we said polystyrene has 90 to 100 Celsius degrees glass transition. Styrene butadiene rubber is a random copolymer. Sorry. Okay, and random copolymers display characteristics in terms of glass transition similar to miscible blends. Okay, molecular blends for a random copolymer is to miscible. So for the random copolymer, for the case of SBr, you can see that we have only one glass transition. And it is around -65, somewhere between these two. Okay. So I want you to remember random copolymers. And miscible blends. One TG, okay, one glass transition. The glass transition depends on essentially the amount of the two phases, the one phase within the other. Okay. Of course, we have different types of copolymers. This is a random copolymer where the alternation between the two phases, the two monomers, is random. Okay, alteration between monomers in the macromolecular chain is random. For the case of block copolymers, we have blocks of monomers bonded with blocks of the other monomer. Okay, so in this case, we have a block of styrene and then a block of butadiene, then a block of styrene, and so on. Okay, in this case, what we create is thermoplastic elastomers, or elastomers. Generally, the use of the word elastomers is much better compared to rubber, because the rubber can point out towards a specific material, which is natural rubber. Well, elastomers points out for the whole family of materials. So if their blocks are long enough, then the styrene parts get together in polystyrene domains, and then we form physical crosslinks. Okay, this is the physical crosslinks that I'm talking about. In this case, we have polystyrene here, and these chains here, these chains are polybutadiene. Okay, so we have a combination of a soft phase and a hard phase as well. And in this case, the cross-linking is physical cross-linking. And you can see that we have again two types of glass transitions, one here and one here. Okay. And now, for the last part of the course on the glass transition temperature, let's look on how do we measure the glass transition temperature. Of course, here I will just introduce you to a couple of experimental techniques, but for the DSE, we will talk more onto the next session, where we use DSE in order to observe both glass transition, melting point, and crystallization temperature. So DSE is a very, very important calorimetric technique, which helps us observe thermal transitions in polymers by heating or cooling them at different rates. Okay, very briefly, how Dse operates is we have a furnace, we have here the sample, and here we have a reference. This is the furnace, let's say. We have the reference here. It's empty. So we increase the temperature or decrease the temperature in the furnace, and we measure the difference in heat between the two samples. Okay. Another very important method to measure the glass transition temperature is by using dynamic mechanical analysis or dynamic mechanical thermal analysis, or some people call it like that. So in this case, we determine the dependency of the modulus of the mechanical properties and the loss angle as a function of temperature, and it can also provide us with significant information regarding the transition temperatures, but only for melting and glass transition, not for crystallization. Okay. And we also have a practical measurement, which is the heat deflection temperature, which we will see in a bit. A dilatometer is a very old school measurement. We will not be focusing a lot on this. It's just a matter of using the volume values for the evaluation of the glass transition temperature. Yep. So this is for the dilatometry measurement, but essentially the dilatometry gives us when it measures the volume. Okay, and by measuring the volume when we transform from a liquid to glass, essentially it tells us at which point we observe the glass transition. Don't worry about dilatometry. It won't be used or requested for you to remember anything regarding dilatometry, so don't worry about it. Let's go on and look upon the DSC. In the DSC, what we measure is essentially the heat capacity, which is the ratio of the enthalpy over temperature as a function of the temperature, or the enthalpy of the system, the heat flow in the system. So this is an idealized situation where the TG, you can see that it is directly 1. Usually the glass transition looks like that, okay, for Cp over temperature. It is a region, let's say, of temperatures, and obviously before the glass transition we have a glassy or glassy behavior, while after the glass transition we have a rubbery behavior of our material. It becomes much softer. I should point out that DSC uses tiny amounts of material. Okay, so we need I don't know, sample sizes in the order of 10 grams or something, which is essentially nothing. No, milligrams, sorry. So yeah, that is how a glass transition look in a TG. I just used this slide in order to point you to not a non-idealized situation. This is a normal situation where essentially this is a glass transition here. Okay, these values here and here, this is considered the onset. This is considered the end set of the glass transition temperature. Okay. And finally, we said that dynamic mechanical analysis is very dynamic mechanical thermal analysis. where it is a technique which helps us. It's very helpful because it helps us identify the thermal transitions in polymers, but also we can keep, let's say, the temperature constant, and we can modulate different types of characteristic in order to observe the parameters such as the modulus of our material. Okay, it can give us the mechanical properties, as a function of temperature or frequency, and can also give us thermal transitions. G. Okay. What does dynamic mechanical analysis do? Essentially, we apply sinusoidal stress, and this is translated to we apply sinusoidal strain, and this is translated to stress. Okay, we strain the material, and this is translated to stress. Strain, stress. Again, this is a graph that we discussed quite extensively. We said that here we have the frozen chains. Here in this region we have the glass transition, and here we have the chain slip that is for a semi-crystalline polymer. Okay. Yep, that is what we said. That is the tan delta. The DMTA can give us information regarding the tan delta, which is given by this peak, where the peak essentially specifies the glass transition temperature of a polymer. We will see more about DMTA in the section of I think it's a section of mechanical properties. I don't remember very well, but we will see we will discuss certainly more during the semester. So don't worry about the technique too much at this point. Just focus on the thermal transitions. Okay. And finally, a practical measurement that is commonly used by industry, not so much from let's say researchers in academia or universities or institutes, is the heat deflection temperature measurements. It's a practical measurement similar to melt flow index, which is used for the measurement of the molecular weight. What happens in the heat deflection temperature is essentially we heat up our material and we apply some pressure on our material. When the material is still stiff, then it won't bulge. Okay, it remains solid. But when it's heated up after a certain point, then the material starts to wrapping. Okay, so it becomes like that because of the increase of temperature. And that increase of temperature, when the material becomes like that, so the curvature, that provides the softening point. And in industry, a softening point can be approximated with a glass transition temperature. Okay, so if we look at in a bit more detail on what we do on heat deflection temperature, is we have our sample here. We immerse it in oil in order to keep in order to know the thermal conductivity of the oil, so we know how much temperature we increase every time, and we apply some force from this stage. So we have a 3-point bending. So we keep the force constant, and with increasing temperature, this material will start to form a curvature. Okay, and because it forms a curvature, This is the softening point, and it is an approximation of the glass transition temperature. Okay, it is very straightforward. It's interesting. It's easy, but it's not, you know, as a you know, in an academic environment, you cannot use heat deflection temperature in order to say, okay, I've measured the glass transition temperature. Okay. And it is very important to know the heat deflection temperature, because in applications such as, I don't know, in a laptop, let's say, we don't want a polymer to heat up to its softening point, and then, you know, once you apply some pressure yourself, then it becomes distorted. Okay, so polymers should not be used above 80% of their heat distortion temperature in order to prevent warpage and distortion. Okay, and we have 3 minutes. If you can please let me know, can you imagine what happens during ironing in the concept of glass transition temperature? What happens during ironing, let's say? Any ideas? So when we use an iron, okay, we give thermal energy to the change of the polymer, because the majority of our clothes are made from, let's say, polyethylene fibers or something like that, or for fibers, polymeric material. Because we provide enough thermal energy for our materials to start for the macromolecular change to start moving, and also we apply force to the chains by pressing them down, okay? What we do essentially is we provide them enough energy in order to soften our material, and with the force, we give them a specific conformation, okay? And because we give them a specific conformation, we straighten out our materials by using, again, thermal energy passing through the glass transition temperature and force. So a combination of the three provides a very straight piece of clothing. Okay, that's it from me for today. Any questions, please feel free to send me a text or an email, and I'll see you again on Thursday, where we will start discussing the rest of the thermal transitions on melting and crystallization. Have a good afternoon, and see you on Thursday. Bye.